Hi, my name is Arpan Kusari. I'm an assistant research scientist at University of Michigan Transportation Research Institute, and I'm presenting a paper on enhancing the capabilities of SUMO simulator for performing effective verification and validation of autonomous vehicles. Autonomous vehicles, or AVs, need to be deployed in real world traffic, for which they need to be validated. As humans, we take a driving test, which helps us certify our ability as drivers given personal liability. But how does the certification process for AV look like? Researchers have shown that for effective testing of AVs, it needs to be driven somewhere in the order of hundreds of millions or to hundreds of billions of miles. Even with large enough fleet of vehicles, it seems like an insurmountable task. So, in what ways can AV developers guarantee safety in various different weather conditions, road geometries, traffic situations? There are three major ways of doing AV testing with different strengths. Simulation provides virtual environments with virtual agents with large amount of control. Closed track testing provides a controlled setup for testing physical AVs, while on-road testing are completely uncontrolled but provide largest amount of real interactions. We will focus on simulation testing in this paper. Simulation provides a large number of benefits, especially in testing all different plausible scenarios and understanding the effect of different parameters on safety and comfort. The biggest challenge is modeling the environment to be realistic. How can errant behavior of other vehicle be modeled? Simulation use cases can be defined neatly into scenarios. There are some different ways of creating scenarios, but the Pegasus model provides a six-layer architecture, which is a convenient way to structure scenarios in a modular approach. As shown in the figure given on the right, we can structure an environment into layers. The first layer is a road network. The second layer are the roadside structures like buildings, etc. The third layer is the temporary modification of L1 and L2, given as the construction sites, road network, road mappings. The fourth one is the dynamic objects, which under which vehicles, pedestrian, trailers, animals, all these come into play. And the fifth one is the environmental condition. So any kind of precipitation, any kind of weather, whether it's rain, sun, rainy, sunny, that comes into play picture. And in the sixth layer is the digital information. So V2X cellular network comes into this one. Our goal is to build these layers to create a complete simulation platform. In this work, we intend to provide enough variability among the driver population representative of the real world. We also intend to enhance ease of use for the end user by abstracting the foundations of the simulator. To do so, we utilize SUMO simulator. SUMO helps in creating road networks from scratch, importing real road network layouts from maps such as OpenStreetMaps, and creating static and dynamic agents and individually controlling them. Although SUMO is great for testing, the background vehicles drive in a predetermined fashion without any variability. Also, it takes a lot of time and effort to set up large-scale simulations. Our overarching solution is to build a six-layer model. Currently, we build the road network and vehicles. We want to induce real-life variability by learning from naturalistic driving data to create vehicles with different driving behaviors. Finally, we abstract the simulation environment using OpenAI Gym, which is known for its accessibility. In real world, all vehicles drive differently. However, in simulation, other vehicles drive passively, keeping safe distances from other vehicles. We utilize naturalistic data collected at our institute to learn parameter distributions from the very popular car following model known as the intelligent driver model, using a Bayesian method called Metropolis Hastings to estimate these distributions. This slide provides the parameters that we estimate. We showcase the results for highway and urban driving parameters in the slide. Given these parameters, we can then sample from them randomly to generate longitudinal driving behavior representative of real-world variability. For ease of use, we notice that the end user can run simulation without building environments or placing vehicles from scratch. Also, for A/B testing, we only need to provide observations of the other neighboring vehicles as output and take the corresponding action from A/B stack as input. This is exactly what OpenAI Gym library seeks to do, and so we adopt it for our purpose. OpenAI Gym is a open source library for training reinforcement learning agents in various virtual environments, as demonstrated by the cart pole and ant environments shown in the right-hand side. The key feature of the library is accessibility for all kinds of users. The left side figure in the slide shows the control structure of our overall architecture, where we create a scenario based on a chosen network and a corresponding learned parameter distribution for longitudinal behavior. We then utilize SUMO as a simulation environment and the environment class to interact with the AV stack. Now on the right side figure, we show how a simple commands can be used to create a viable user interface for simulation. The commands in this case being reset, step, and render and close. In this slide, we showcase the results of our simulation environment with longitudinal behavior given by IDM and a simple lane changing model. As you can see, it performs autonomous lane changes. Thank you. The GitHub is given below.